Okay, we'll continue talking about semiconductors. Let me remind you with the basics. A semiconductor is characterized by the fact that its electrical resistance is decreased by raising temperature or by doping, addition of certain impurities. And now talking about the action of the transistor. As I said, it can act as a switch, fast switch, and signal amplification. Okay. Transistors act as fast switches and as amplifier. These are the two main functions of the transistor. Okay. In front of you here, we are talking about NPN transistor. Okay, and it's connected to the positive terminal of 6-volt battery. Emitter is connected to the negative terminal. Will you please pay attention to something, to the junction between collector and base. And what about the collector? Let's take it one by one. Collector is N-typed. It is connected to the positive terminal. Okay, so it is reverse biased. In this case, I don't expect at all the current to flow from the emitter to the collector. I don't expect the current to flow from the emitter to the collector because we've got a region which is reverse biased and it forms high resistance. Once again, your attention, talking about the collector and base. Collector is N-typed and it is connected to the positive terminal. N-type to the positive, it is reverse biased. So we expect, yes, a depletion layer, a resistance which does not allow the passage of the current. So no current flows in such a case. Okay. We've got, as I said, reverse biased junction. Okay. And now what happens? We'll do something a little bit different now. What happens when the base is connected to the positive terminal of 0.6 volt battery? Okay, we want to understand the action of the transistor. To understand it, there is two currents. One which is small current but dominates the other one. The current, okay, from the emitter to the base, and we can say base emitter current dominates the collector emitter current. Okay, let me say it in a simple way. So as to obtain a collector emitter current, there must be a flow of current, okay, from the base to the emitter. So what happens now? Your attention, please. The base is connected to the positive terminal. What really happens? Okay, electrons which diffuse from N-type into the P-type base, some of them, okay, neutralize with the holes. Okay, but when the base is connected to the positive terminal, this positive terminal, 0.6 volt positive, will be able to extract these electrons from holes. And this will give the chance, for further flow of electrons from the emitter to the base and then through to the collector. So this is very important to understand it. Let me say it again. To understand the action of the working action of the transistor, there are two currents. A small current which dominates the majority current, okay? The current from the emitter to the base, yes, dominates the passage of the current from the emitter to the collector. Okay, if the 0.6 volt is not connected, what really happens? Some electrons from the emitter neutralize some holes, okay, and will get a cease, a stop of flow. But when the base is connected to the positive, what happens? The positive terminals will extract electrons from the holes, and this will give the rest of electrons to push, give them the chance to push, to move, to pass the base into the collector. And don't never forget, emitter current is equal to base current plus collector current. Okay, once again, now I'm talking about the electron flow. Don't never forget, the base should be connected to positive 0.6 volt to extract electrons from the holes and to give further a chance for the electrons in the emitter to pass to the collector. Okay. And we can demonstrate this in a very simple way. Okay, look at this and try to look at this image and try to figure it out. Okay, we've got a passage of few persons here, but this passage through of these few persons through the gate, yes, raises the door of the collector to allow the current of the emitter to flow. This is very important. So we've got a small current, but actually it dominates the passage of the majority current. Okay, this is the action of the base. So if IE is the emitter current, IE is the emitter current, alpha E is the fraction of the emitter current that reaches the collector. Let me explain this. IE is the emitter current, alpha E is the percentage. 97% of the emitter current reaches the collector. So I can say IC, current of the collector, equals alpha E times IE. IE is the emitter current, then alpha E is the fraction of the emitter current that reaches the collector. Okay. Once again, emitter current equals base current plus collector current. Okay. So base current, of course, it's all easy, equals emitter current minus collector current. So what about the collector current? It is 90 or 98 or 97% of the, yes, emitter current. So it is equal to alpha E I emitter. Okay, now we can do something. We can take emitter current as a common factor. So I base equals IE, between two brackets, 1 minus alpha E. Let me remind you with something. Alpha E is the fraction of the emitter current which reaches the collector current. That is to say, IC equals alpha E I emitter. Current of the collector equals 90% of the current of the emitter, simply because the rest flows through the base. And it is always right that the emitter current is equal to base current plus collector current. Okay, your attention. Now we managed to obtain current of the base. It is there. We consider it input. Current of the collector, we consider it the output. So we'll do something interesting right now. If we regard base current as the input current and IC as the output current, so now we can understand the transistor can act as, yes, first of all, it can act as a switch. How? Simply because I said there is a current essential, a current that must flow so as to let the emitter current pass through the collector, current of the base. So if the current of the base, a switch in which current of the base turns on, the current and controls the current of the collector. If current of the base equals 0, no current flows to the collector. Okay. If current of the base once again equals 0, no current flows to the collector. IB equals 0, IC equals 0. Okay. When the voltage of the base is connected to a voltage roughly equal to 0.6 or 0.7 volt, what happens? Yes, we've got a base current and current flows through the collector. IB starts to flow, thereafter IC increases when IB. And a small increase in base current will cause, yes, a large increase in collector current. So the second action is, we want to understand the second action of the transistor. It acts as an amplifier. Why? I've just mentioned it. A current amplifier, it acts as a current amplifier since IC is much greater than IB. Output is much greater than input. And a small change in base current causes tremendous change in collector current. Okay. And now we'll obtain something we call current gain. What about current gain? It is denoted by beta E. Okay, well, let me remind you with alpha E. Alpha E is the fraction of the emitter current which reaches the collector. But beta E is current gain. It is the ratio between output current, current collector, and input current, current of the base. Okay. Current of the collector, it is a fraction of the current of the emitter. Alpha E times current of the emitter. And we managed to obtain current of the base to be equal 1 minus alpha E between two brackets times IE. Of course, IE will be cancelled out, crossed out. So current gain, and you'd better memorize this. This is very important in solving problems. Current gain equals alpha E over 1 minus alpha E. And now I'm going to explain in details how the transistor can act as a switch. Okay? Your attention please, because I'll show a circuit. Okay? In front of you it is shown right now. What about this circuit? You'll notice that we use the symbol of the transistor, and we want to know what type of the transistor. Is it NPN or PNP? Okay, you can know the type of the transistor from the direction of the arrow drawn on the emitter. Okay, it is directed outwards, so we've got NPN. Okay, your attention please, talking about, what about VCC? And it is actually 6 volt. It is equal to the sum of potential V out or VCE and IC plus RC. Let me explain something. RC is the resistance of the collector. IC, current of the collector. Product of RC and IC will give a voltage on the collector. Okay, in addition to the voltage on the CE, collector emitter, both of them will add to give VCC. So VCC equals VCE, voltage across collector emitter, and IC RC. Okay, sum of two things equal to a constant. A plus B equals a constant K. For example, A plus B equals 12. A, if it is 2, B should be 10 to give 12. If A increases to be 4, okay, B should be decreases to be 8. So we've got a reverse, yes, an inverse relation between VCE and ICRC. If VCE increases, IC/RC decreases. Why? Because the sum of them will give VCC. Okay, your attention please. I'm explaining how it will act as a switch. Okay, to turn on and off. If we don't have a cell here, what happens? Okay, we said we have no current in the base. No current flows through the base, no current flows through the collector. So IC equals 0. What happens when IC, and now if we added a cell, a current is drawn through the base. A current flows through the base, and a current, much greater current, flows through the collector. Okay, so what happens? Yes, IC increases, so the product of IC RC increases, and this means VCE should be decreased almost to be equal to 0. This happens when the base is connected to the positive terminal. A current flows through the base. Current flows through the base, causes large current to flow through the collector. IC increases, product of IC RC increases, so the output volt should be decreased, and it will be diminishing to be equal to 0. So I managed to switch it off. Yes, the base is reverse biased. No current passes through the base. So no current passes through the collector. IC equals 0. So IC RC equals 0. So VCC is almost equal to V out, or equal to VCE. Okay. That is to say, when the base voltage is too low or negative. Okay, your attention please. When the base voltage is too low or negative, the transistor is off. Great. And the collector current is very small, and the output voltage on the collector is high. And now talking about logic gates. What about logic gates? Okay. Logic gates are the circuits that perform logic operations. Let me say it again. Logic gates are the circuits that perform logic operation. The first gate, we call it the inverter or NOT gate. Your attention please, because this is very important. I'm talking about gates which are based on transistors. Okay, the first is the NOT gate. We call it inverter. What about the inverter? NOT gate. It is given this symbol of an arrow. It has one input and one output. It has one input, as I said, and one output. Okay, this is the NOT gate. Okay, what about its function? It can be simplified by this electrical circuit. Okay, gates are electronic components, but it can be simplified, understood by the electric circuit shown in front of you. Okay, let me explain this circuit, and it is quite simple, and I believe you know it quite well. Okay, now we've got a lamp which is connected to a cell and resistor, and in between, okay, we've got a wire and a switch, wire of no resistance and a switch. Okay, your attention, if the switch is closed means gives 1, the current will take the easiest way. No current will flow through the lamp. So the lamp will glow off, will be given 0. Okay, so let me take it one by one. Okay, input is the switch. And what does it mean? It is given 1, it is closed. What happens when I close the switch? I'm depriving the bulb from the current. So it is equal to 0. So it is inverter connected. It inverts from 1 to 0. If it is switched on, no current will flow through the bulb, so it will be given 0. Okay, what happens if we open? Switch is open, it is given the symbol 0, the current will flow through the bulb, so it will be 1. So the NOT circuit converts 1 into 0, converts 0 into 1. So that is why we call it inverter. Okay, and in front of you is the electrical circuit that simplifies the action of this gate. This was about the first gate, and it was quite easy. The second one, okay, is the AND gate. What about the AND gate? Your attention, please. What about the AND gate? This is the symbol, and you should memorize it quite well. This is the symbol of the AND gate. It has one output and it has two inputs or more. It could be 3 or 4, okay, but just one output. Okay, we'll understand the logic behind this gate, AND gate, okay. To understand this, we need an electrical circuit, of course. And now we have two switches which are connected in series, switch A and B, okay. They will demonstrate the action of the AND gate, okay. Don't never forget, as I mentioned before, transistor can act as switches. Okay. Now, your attention, it is quite clear. For the lamp to glow, we need to close both of them, A and B. Close means it will given, yes, 1. 1 for A and 1 for B. We'll take it one by one. We'll understand the truth table. Okay. What about the probabilities we've got here? If A, yes, A is equal to 0, what does it mean? The switch is open. B is open. Of course, no current will reach the lamp, so it cannot flow. Yes, so the bulb will not glow. Okay, so all will be 0. And now, what if I open one of them, A, and close the other? B is closed. Closed, it is given 1. But still the current cannot flow to the bulb. So the result is 0 still. Okay. And other possibility, A is closed. B is open. Also no possibility for the current to reach the bulb. It won't glow, 0. So for the bulb to glow, both of them should be equal, or each one of them will be equal to 1. Both of them should be closed. In this case, we'll reach 1. This was about the AND gate. And the last one is the OR gate. What about the OR gate, and how can we simplify it by using an electrical circuit? This is the first symbol of the OR gate. It has 2 inputs or more and just one output. And you should memorize how to draw it quite well. And we'll understand the truth and the logic behind it. Okay? We need a circuit, electrical circuit. Now the 2 switches are connected in parallel. So just one path is closed, will permit the flow of the current to the bulb. Okay. Now we've got 2 switches, but not connected in series, in parallel. And what about the truth table? A demonstrates first switch, B demonstrates the state of the second, and the output is demonstrated by the bulb. Okay. First probability, both of them are open, 0, 0. Of course, no current reaches the bulb. Okay. And now, if A is open, but B is closed, okay, the current will find the path to reach the bulb, so the bulb will glow. Okay. And what about other possibilities? A is closed, B is open. Okay. Also, we expect to have it. Yes, the current will find the path to reach the bulb, so it will glow. And what if both of them are closed one on one? Of course, we'll glow the lamp. Okay, this was about the truth table of the OR gate.